Hello there, and welcome to the Sleepy Science Channel. Tonight, we're stepping into a world of bright colors, sweet fragrances, and familiar shapes resting quietly in bowls. Fruit is not simply food. It is a living invention millions of years in the making. Every apple, every berry, every citrus slice is the result of a delicate partnership between plants and the creatures that carry their seeds. Sugars are crafted with care. Colors are tuned for the eyes of animals. And fragrant smells are released at just the right moment. Beneath the softness and sweetness lies chemistry, timing, and survival. From ancient forests to modern markets, fruit has shaped ecosystems, guided migrations, and even influenced human history. It connects flowers to animals, continents to climate, and your own body to the long story of evolution. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften and allow your breathing to slow. And allow your mind to settle as the day begins to gently fade away. Join me on this fascinating journey through the natural world. Let's begin. Fruits are how plants bribe animals to carry their seeds. A plant cannot walk its children to new ground, so it makes an offer. It wraps seeds in sweetness, color, and scent, then waits for an animal to accept the deal. In exchange for calories and water, the animal carries seeds away from the parent plant, often to a place with more light, fewer pathogens, and less competition. This trade can shape entire landscapes. A hedgerow full of berries can guide bird movements like a living road. A grove of fruiting trees can pull animals across valleys, then scatter new seedlings wherever they pause. Even the timing matters. Many plants concentrate ripening into short bursts so animals show up in crowds and seeds get dispersed quickly. It is commerce without coins. The currency is sugar and fragrance, and the delivery service has wings, paws, and patience. Avocados once relied on giant Ice Age mammals to spread. An avocado has a huge seed and a thick, rich layer of flesh, which is an odd combination if your only seed carriers are modern birds and small mammals. One idea is that it made perfect sense when North and Central America had giant fruit eaters. Think of massive ground sloths and gomfothers, which were elephant-like. They could swallow large fruits whole, walk miles, and leave seeds behind in ready-made fertilizer. When those animals vanished, the avocado's original delivery system likely vanished with them. The tree did not disappear, but its range may have shrunk, and its seed became harder to move around. Humans stepped into that missing role. We planted pits, carried fruit across landscapes, and turned a once risky strategy into a global staple. In a way, guacamole is a rescue story written by extinction and agriculture. A pineapple is a whole bouquet of flowers fused together. A pineapple begins as a cluster of many small flowers packed tightly on a single stalk. As each flower is pollinated, its tissues start to swell, and the whole group grows into one unified structure. Over time, the boundaries blur, and what was once a bouquet becomes a single heavy fruit with repeating patterns on the skin. Each little hexagon hints at a former flower. The spiky crown on top is not decoration. It is a living extension of the plant, and it can be used to grow a new pineapple if it is rooted. Pineapples also show how plants can build big rewards by cooperation rather than by size. Instead of one flower doing all the work, many flowers contribute their parts, then merge their efforts into a single package that animals can spot and carry. Citrus peels hide tiny oil glands that burst into fragrance. If you twist an orange peel near a light, you can sometimes see a mist of oil spray into the air. That scent comes from tiny pockets in the rind, each one a small reservoir of aromatic compounds. When the peel is squeezed or torn, the pockets rupture and release a concentrated burst that travels fast. For the plant, those oils can discourage microbes and deter some hungry mouths. For us, they create that bright, clean smell that feels like instant freshness. The oils also explain why citrus zest has such a powerful flavor compared to the juice. It is chemistry stored in capsules, designed to sit safely under the skin until the moment pressure breaks it free. Even the snap you hear when peeling a tangerine has meaning. It is a protective coat opening and a cloud of plant-made perfume escaping on cue. Fruit colors are signals, evolved to recruit animal couriers. Color is not just decoration. It is communication. Plants cannot walk their seeds to new ground, so they often hire animals instead, and bright color is one way to make the offer impossible to miss. Reds, blues, and purples stand out against green leaves, especially to creatures that can judge ripeness at a glance. A fruit that is still hard or unready may stay green and blend in, which reduces the chance it will be eaten too soon. When the seeds are ready, pigments surge, and the fruit becomes a billboard that says, "Now." Different animals respond to different palates, so local fruit colors can reflect local couriers. Many berries aim for birds, which are excellent long-distance carriers. Other fruits appeal to mammals, which may spread seeds in different patterns. Every bright cluster in a tree is a message written in pigment, aimed at a moving audience. Many seeds on a strawberry are separate little fruits. Those crunchy dots on the outside each have their own story. Instead of one fruit holding many seeds, a strawberry is a collection of many tiny fruits, and each one is called an aken. Inside each aken sits a single seed, wrapped in a hard shell that can handle bumps, bites, and weather. The strawberry's red flesh is the stage that presents them, and the plant uses sweetness, aroma, and color to convince an animal to pick it up. As the animal eats, the akens hitch a ride, often traveling far from the parent plant. This is seed dispersal disguised as dessert. It also explains a subtle texture you may have noticed. The seeds feel separate because they are separate. You are tasting a many-fruit structure working as one, with every dot acting like a tiny suitcase for the next generation. Apples can ripen other fruit by releasing ethylene gas. Ripening is not only about time. It is also about signals, and one of the biggest signals is ethylene, a simple plant hormone released as a gas. Apples produce it in noticeable amounts, which is why an apple in a bowl can speed up the softening and sweetening of nearby fruit. Inside a fruit, ethylene triggers enzymes that change texture and flavor. Starches convert into sugars. Cell walls loosen. Aromas deepen. This is incredibly useful in nature because coordinated ripening makes fruit more likely to be eaten at the right moment. For people, it becomes a quiet kitchen trick. If you want a firm avocado to soften, placing it near an apple can help. If you want berries to last longer, keeping them away from ethylene producers can slow change. The apple is not only food. It is a tiny chemical broadcaster, sending ripen now messages through the air. The tomato is a fruit because it develops from a flower ovary. That definition sounds small, yet it reshapes how you look at a garden. After a tomato flower is pollinated, the ovary swells and becomes the familiar red flesh, while the ovules inside become seeds. That is the botanical rule for a fruit. The vegetable label is culinary because we tend to cook tomatoes with savory foods rather than treat them like dessert. Slice one open and you can see the logic in its chambers, where seeds sit in gel that helps protect them and keeps them hydrated. Different varieties exaggerate different parts of the same structure. Paste tomatoes lean toward thick whorls, while cherry tomatoes lean toward juicy seed pockets. A tomato is the flower's plan continuing after bloom, turning reproduction into something bright, edible, and easy for animals to carry. Botanically, a strawberry is not a true berry. In plant science, berry has a surprisingly strict meaning. A true berry forms from a single flower ovary, and the seeds end up embedded inside a fleshy whorl. Strawberries take a completely different route. The red part you bite is mostly swollen flower tissue that grew after pollination, like the plant building a soft pedestal to show off its real payload. Those tiny specks on the outside are not seeds in the usual sense. Each one is its own little fruit, with a seed tucked inside, carried on the surface like a field of miniature capsules. This mismatch is why strawberries feel like they are breaking the rules. They look like the perfect berry, yet their structure tells a very different story about how flowers turn into food. Botanically, a banana is a true berry. Bananas fit the botanical definition with almost shocking accuracy. They develop from a single flower ovary, and the ovary wall becomes the soft, edible flesh. The seeds, in wild bananas, sit inside that flesh, which is exactly what a berry is meant to do. The bananas we usually eat feel seedless because humans selected varieties where the seeds never fully develop. Over time, that turned the fruit into something smooth and easy to eat, and it also made it dependent on people for reproduction. Farmers grow new banana plants from cuttings rather than from seeds, which means entire plantations can be closely related. That gives bananas their reliable taste and texture, but it also makes them vulnerable to disease, since a threat that can harm one plant can often harm many. A true berry, yes, but also a lesson in trade-offs. Every apple fruit is built from the flower's swollen base. An apple is like a floral illusion, because most of what you eat did not start as ovary at all. After pollination, the flower's base swells dramatically and becomes the crisp, juicy part we call the apple. The true ovary becomes the core, including the papery chambers that hold the seeds. This is why slicing an apple across the middle reveals that star shape. It is the hidden architecture of the original flower, preserved inside the finished fruit. Apples belong to a group called palms, which includes pears, and they all share this clever construction. The plant ends up building a sweet protective jacket around the seeds, while keeping the seeds safely sealed in the center. Once you notice it, every bite feels like eating a transformed blossom, not just a snack. Some figs are pollinated by one specific wasp species. A fig is not a simple fruit with open flowers. It is a closed structure with tiny flowers hidden inside, which means pollination needs a specialist that can enter. In many fig species, that specialist is a particular fig wasp, matched to that fig alone. The wasp slips through a small opening, carrying pollen from another fig, and pollinates the hidden flowers as it moves inside. In return, the wasp can lay eggs in some of those flowers, which become a nursery. This partnership can be so precise that if either partner disappears from an ecosystem, the other may struggle to reproduce. It is one of nature's most intimate agreements. The sweetness we associate with figs begins as a private transaction in a tiny chamber, where a plant and an insect rely on each other with extraordinary cane. Specificity. Some fruit only tastes sweet after it escapes a predator's gut. For certain plants, the main goal is not to please every mouth. It is to get seeds delivered safely to a new place. Some seeds are wrapped in tough coats, and the plant benefits when an animal eats the fruit, carries the seeds, and passes them later. During that journey, the fruit's sugars and starches can be broken down, and the remaining pulp can ferment slightly. Once it leaves the animal, the scent and taste of what is left can shift, And that can attract a second wave of creatures like insects or dung beetles that move seeds again. It is a relay race, with one animal doing transport and another helping with burial or spreading. To us, the idea sounds strange, yet it highlights how plants can design fruit for an ecosystem, not for a single eater. In nature, sweetness can be timed for after the ride. Grapes can be fermented by wild yeasts living on skins. A grape skin is a busy surface, even when it looks perfectly smooth. In vineyards, microscopic yeasts settle onto that waxy coating from wind, insects, and the local environment. When grapes are crushed, juice meets those yeasts, and sugar becomes fuel. If no commercial yeast is added, fermentation can begin on its own, sometimes within hours. Winemakers call this spontaneous fermentation, and it can produce wines that feel tightly linked to a place, because the microbial community is part of the local signature. It is also unpredictable. One batch may race ahead while another slows, and the aromas can shift in surprising directions. This is why some winemakers treat fermentation like listening rather than forcing. The grape brings sugar and juice. The vineyard brings microbes. Together, they create a transformation that feels almost alive. A single watermelon can hold hundreds of seeds, each a future plant. A watermelon is a giant investment, and the seeds are the real reason it exists. Each seed carries an embryo plus a packed lunch of stored energy, sealed inside a tough coat. By the time the fruit is fully ripe, the plant has already poured weeks of sunlight into building that seed army. The sweet flesh is the advertisement that convinces an animal to take a bite, and the water content is not just refreshing. It helps keep the fruit inviting in hot, open habitats where dehydration is a threat. In the wild, a cracked rind can become a feeding station, and seeds spill into the soil nearby or travel farther in an animal's wake. To us, seeds can feel like an inconvenience. To the plant, they are a strategy multiplied hundreds of times, betting that at least one will land in the right patch of ground. Peppers are fruits, even when they feel savory. In the plant world, flavor does not decide what a fruit is. Structure does. A pepper forms after a flower is pollinated, and the swollen ovary becomes the walls you slice, roast, or crunch. Inside, seeds cling to a pale central tissue, and that inner scaffolding is where many varieties concentrate their heat compounds. This means a bell pepper and a fiery chili are built on the same basic blueprint, despite tasting like they belong in different worlds. That blueprint also explains why peppers can change dramatically as they mature. Green peppers are often simply unripe versions of the same fruit that later turns red, yellow, or orange. The plant is not switching categories. It is finishing the ripening schedule. Once you notice that every pepper began as a blossom, the produce aisle starts to look like a gallery of flowers that learned how to travel. Cucumbers are fruits because they form around seeds. A cucumber begins as a flower on a vine, and after pollination, the ovary elongates into that familiar cylinder. Botanically, it is a fruit, and more specifically a type called a pipo, which is common in the gourd family. This is why cucumbers are close relatives of melons, pumpkins, and squash, even if they end up in salads. Their crispness comes from cells filled with water under pressure, like tiny balloons packed together. When you bite, those cells rupture and release a cool snap that feels almost engineered for refreshment. Inside, the soft seed core is a nursery that develops as the outer wall keeps growing. In some varieties, that seed core stays tender and mild. In others, it grows firmer with age, which is why older cucumbers can taste stronger and feel more seeded. It is a fruit built for speed and hydration. Vanilla is a fruit, a long pod from an orchid. Vanilla begins with an orchid flower that opens for a short window, then quickly fades. If it is pollinated in time, the ovary stretches into a long green pod, and that pod is the fruit. What we call vanilla beans are not beans at all. They are the tiny seeds inside, surrounded by fragrant pulp that develops during curing. Fresh pods have very little of the familiar aroma. The magic comes later, through careful drying and sweating that coax new compounds into existence. In places where the natural pollinator is absent, many vanilla orchids are pollinated by hand, flower by flower, which is one reason vanilla can be so precious. It is also one of the clearest reminders that flavor is often a process, not a single ingredient. A delicate orchid turns into a fruit, and the fruit turns into a scent that can fill an entire room. Coffee beans are seeds from a red fruit called a cherry. Coffee starts as a small, shiny fruit that often ripens to red, and growers call it a cherry. Inside are usually two seeds facing each other, each wrapped in layers of pulp, sticky mucilage, and a papery skin. Those seeds become the coffee beans after processing removes the fruit. This means every cup begins as a harvest of fruit, not a harvest of beans. The way that fruit is handled shapes flavor long before roasting. In a washed process, the fruit is removed quickly to highlight clean, bright notes. In a natural process, the cherry is dried around the seeds, and sweetness can deepen as the fruit sugars influence fermentation. Even the discarded fruit has a name, cascara, and it can be brewed into a tea-like drink. Coffee is often treated like a purely roasted taste, yet its first life is as a juicy fruit designed to be eaten. Cacao beans come from a tropical fruit, not a nut. Cacao grows in large pods that hang from the trunk and thick branches, and each pod is a fruit filled with seeds. When the pod is opened, the seeds come out coated in a pale, sweet pulp that smells surprisingly fruity. Those seeds only become chocolate through a careful chain of transformations. First comes fermentation, where microbes break down pulp and kickstart flavor precursors inside the seed. Then drying slows decay and stabilizes the chemistry. Roasting later deepens aroma and drives the familiar chocolate notes to the surface. Without those steps, cacao seeds taste bitter and astringent, more like a raw ingredient than a treat. This is why chocolate is a crafted food even before the factory stage. It begins in a humid orchard with a fruit that must be opened at the right moment, then guided through microbial change. In every chocolate bar, there is a hidden fruit story. Olives are fruits, packed with oil for a seed's first meal. An olive is a drupe, which means it has a fleshy outer layer and a hard stone protecting a single seed. That seed is valuable, and the tree stocks the surrounding flesh with energy in the form of oil. For the plant, oil is dense fuel, and for us, it becomes one of the most important foods in human history. Fresh olives are usually too bitter to eat because the fruit is loaded with defensive compounds that discourage casual snacking before the seed is ready. Curing changes that. Salt, water, thyme, and sometimes fermentation help soften bitterness and reveal the olive's deeper flavors. Pressing the fruit separates oil from water and solids, turning a seed support system into a liquid ingredient that can travel far beyond the tree's range. An olive is not just a garnish. It is a fruit built to store sunlight as oil, then released through human ingenuity. Seed coats can survive acid, thanks to tough protective chemistry. When an animal eats fruit, the seed faces a brutal obstacle course. Teeth crush, stomachs churn, acid dissolves. Many seeds survive anyway, because their coats are built like armor at a microscopic scale. Layers of hardened cells, waxy barriers, and tightly packed fibers can keep acids from reaching the embryo. That protection is not only survival, it can be a trigger. The trip through a gut can weaken the coat just enough to let water in later, which helps the seed sprout at the right time. Some seeds even travel farther, because gut transit takes hours or days, turning an animal's daily wanderings into a dispersal map. From the outside, eating fruit looks like a simple meal. For a seed, it can be a carefully designed voyage through darkness, chemistry, and motion. Some seeds only sprout after fire cracks their dormancy. Fire sounds like the enemy of life, yet for some plants, it is the starting gun. In certain landscapes, heat, smoke, or the sudden change in soil chemistry tells a seed that the competition has been cleared. Flames may remove leaf litter, open sunlight to the ground, and release nutrients from burned plants, creating a rare window for seedlings to thrive. Some seeds have coats that resist water until heat creates tiny cracks. Others respond to chemicals in smoke that drift into the soil after a burn. The seed can wait for years, even decades, holding its embryo in a safe pause. Then a fire passes, and a whole hillside can shift from quiet to crowded with new growth. It is not resilience by accident. It is a life cycle that includes catastrophe as a normal season. Berries often ripen fast to beat rot and hungry rivals. A small, juicy fruit has a problem. It is delicious to animals, and it is also delicious to microbes. Once it reaches peak sweetness, decay begins to race. Many berries solve this by ripening quickly and loudly, then relying on rapid removal. A bush may shift color across dozens of fruits in days, turning into a brief signal that pulls in birds, mammals, and insects. That rush is not chaos. It is strategy. The faster a ripe berry gets eaten, the less time molds and fruit flies have to turn it into waste. Fast ripening can also outcompete neighboring plants. If your berries become irresistible first, the local birds may fill up on you before they visit the next hedge. The result is a short, intense season where every ripe berry feels urgent, as if the plant is saying, now or never. Fruit sugar is energy for animals, but also a seed's advertisement. Sugar tastes like comfort because bodies evolved to value quick energy. Plants exploit that preference with remarkable precision. As a fruit ripens, it often converts stored starch into sugars that dissolve easily on the tongue, then releases aromas that promise the same reward. This does more than feed an animal. It changes behavior. A monkey may remember a particular tree and return at the right season. A bird may switch routes to check a berry patch daily. That attention is valuable because it turns a stationary plant into a destination. The seed benefits when the animal eats and leaves, carrying the future elsewhere. In this light, sweetness is not generosity. It is messaging. The fruit is a bright, edible sign that says, "Come here, take this, and move on." Every sugary bite is a tiny contract between species, written in biology. Fruit scent is chemistry, tuned to the noses of local eaters. Before you taste fruit, you usually smell it. That first hint is a cloud of volatile molecules, and plants can mix those molecules like musicians choosing chords. A ripe peach smells different from a ripe lime because each plant is aiming at a different set of noses and habits. Scent travels in the dark, through leaves and around corners, so it can attract animals before color is even visible. It can also work as timing. Many fruits release stronger aromas when seeds are ready, and weaker ones when they are not. In forests, scent can guide bats and other night-active animals that rely less on color. In open habitats, scent can help an animal locate fruit from far away, saving time and energy. What feels like a pleasant smell in your kitchen is also a targeted broadcast, shaped by evolution to meet the sensory world of local wildlife. Some fruits turn red because primates see red especially well. Color is not chosen for beauty. It is chosen for being noticed by the right eyes. Many primates can distinguish red from green with unusual sensitivity, which makes red fruit stand out against foliage like a lit signal. This can become a partnership. The plant benefits from having its ripe fruit found quickly, and the primate benefits from locating energy-rich food without endless searching. Over long stretches of time, that relationship can push fruit colors toward shades that match primate vision. It is a reminder that the look of a forest is partly shaped by who is watching. When you spot a red fruit glowing among leaves, you are seeing a message meant for a creature like you, built for daylight foraging and quick decisions. In a sense, your eyes are part of the story. The fruit evolved to be found by minds that remember and hands that carry. Some fruits turn purple and black, signaling peak ripeness to birds. Bird vision can be astonishing, and many birds are experts at finding ripe fruit. Dark colors like purple and black can read as a clear cue against green, and on some plants they appear right when the fruit is at its sweetest and softest. That timing matters because birds are powerful couriers. They can travel far in a day, cross rivers and cliffs, and drop seeds into fresh territory. Dark pigments can also serve the plant in another way. They can protect fruit tissues from intense sunlight as sugars build, which helps the fruit survive long enough to be eaten. When a flock discovers a patch, the harvest can be swift. Branches shake, beaks pluck, and seeds begin their journeys in minutes. What looks like a simple color change is a precise signal aimed at travelers with wings, built to spread a plant's future across the map. Wild fruit is often smaller because plants invest carefully. In the wild, every gram of sweetness costs the plant energy and water. A tree that overinvests in huge fruit may leave itself weaker against drought, pests, or a bad season. Smaller fruit can be a safer budget. It still tempts animals, yet it spreads risk across many units. If a storm knocks some fruit down, others remain. If insects spoil a cluster, the plant has more chances elsewhere. Smaller fruit also fits different couriers. Tiny berries are perfect for birds that swallow quickly, while larger fruits may demand fewer, bigger animals. In cultivation, humans reward size, so plants are selected for extravagance. In the wild, nature often rewards balance. The fruit is large enough to be noticed, but not so large that it endangers the parent. A small wild berry is not a failure. It is careful engineering under real constraints. Domestication made many fruits sweeter by reshaping plant priorities. When humans began saving seeds from the tastiest plants, acquired pressure took hold. Plants that invested more in sweetness and softer textures got replanted, protected, and spread. Over generations, traits that helped seeds survive harsh conditions sometimes mattered less than traits that pleased people. Bitterness faded, fibers softened, flesh thickened. In some cases, seeds shrank or became less viable because humans no longer needed the plant to reproduce on its own. Agriculture also changed the fruit's audience. Instead of persuading birds or mammals, the fruit only had to persuade shoppers and farmers. That shift can make modern fruit feel almost designed, because in a sense, it is. It reflects thousands of small choices made by hands and taste buds. Domestication is not only about making fruit sweeter, it is about turning a wild survival strategy into a human-centered partnership, with flavors shaped by culture as much as climate. The world's favorite dessert fruit is also a botanical berry, bananas. Across markets, lunchboxes, street stalls, and hotel breakfasts, this familiar curve shows up again and again. Part of its success is pure convenience. It comes in its own wrapper, it travels well, and it offers quick energy with a soft texture that works for toddlers and elders alike. In many places, it is one of the most affordable fruits you can buy, which makes it a quiet staple rather than a rare treat. It also fits into countless food traditions. It can be eaten fresh, dried, blended, baked, or fried, and it can move from sweet to savory without feeling out of place. Even the smell is gentle, which helps it appeal to people who avoid sharp, acidic fruit. A single plant can produce heavy bunches, and that high yield helped make it a global companion to tea, coffee, and everyday life. The banana most people eat is sterile and seedless. The smooth slice you know is the result of a reproductive shortcut. Many edible bananas develop without making mature seeds, which means the fruit can form even when the usual seed-making process does not finish. In wild relatives, the interior can be packed with hard seeds that crunch like pebbles, and eating becomes work rather than pleasure. In the common eating types, the plant's energy goes into soft flesh instead of hard seed. This changes how bananas are grown. Farmers do not plant a handful of seeds and wait for new combinations. They start new plants from living pieces of existing ones, which keeps the fruit consistent from harvest to harvest. That consistency is wonderful for kitchens, but it makes improvement slower because breeding new types is difficult when seeds are scarce. The banana you peel is a fruit shaped by biology and then amplified by human selection for ease. Seedless grapes are grown from cuttings, like botanical cloning. A seedless grapevine is often continued by taking a piece of stem and persuading it to grow roots, so the new plant is essentially a continuation of the old one. This is why vineyards can keep a beloved variety going for generations, even though the grapes themselves do not provide useful seeds. It is also why grape varieties can feel like personalities. A vine carries a stable identity, and growers can reproduce that identity with remarkable reliability. To create seedless grapes in the first place, growers may start with vines that naturally produce tiny, undeveloped seeds, then select for fruit that stays ND, tender and pleasant. In some cases, young embryos are rescued in a lab, so a new vine can be produced, even when the seed would not normally mature. When you eat a seedless grape, you are tasting a plant line kept alive by careful copying. A navel orange is a twin fruit, grown inside itself. The little belly button at the blossom end is not a scar, and it is not a seed opening. It is a second, tiny orange that started developing inside the first. This happens because of a natural mutation that turns part of the flower into an internal fruit. The result is a sweet orange that is easy to peel and usually has no seeds, which makes it feel almost designed for snacking. That same mutation also means navel oranges do not usually reproduce true from seed, so they are propagated by grafting. A grower takes a small piece of a navel orange tree and attaches it to a compatible root system. Then the new tree grows fruit identical to the parent. In other words, the navel orange is both a fruit and a living copy of an old accident in a single tree, preserved because people loved the result. Many modern apples are grafted, not grown true from seed. If you plant seeds from a delicious apple, you will not reliably get the same apple again. Each seed is a new genetic roll of the dice, and the fruit can come out tart, bland, tiny, or oddly textured. To keep a variety consistent, growers use grafting. They take a cutting from the desired apple tree, then join it to a root system chosen for strength, size control, or local resilience. The top part decides the fruit's character, and the bottom part helps the tree handle soil, drought, or disease pressure. This is why apple varieties can remain stable over long periods, even though their seeds would create endless surprises. It also means an apple orchard is a kind of curated library. Each tree is a chosen variety, carried forward by joining living tissues rather than by starting from scratch. The apple in your hand is often a deliberate continuation of a known favorite. One apple tree can carry several varieties by grafting branches. Imagine walking up to one tree and picking different apples from different branches. This can be done by grafting multiple scions onto a single root system, turning one trunk into a small orchard. Home gardeners do it to save space, and orchardists sometimes do it to improve pollination, since having more than one variety nearby can boost fruit set. A multigraft tree can also extend the harvest season. One branch may ripen early, while another ripens later, which spreads delight across weeks instead of days. It is also a living lesson in plant compatibility. The graft only succeeds when tissues align and the tree accepts the new branch as its own. Over time, the seams can become almost invisible, and the tree grows as a unified organism with multiple identities. It feels like magic, yet it is careful horticulture, using the tree's natural ability to heal to create variety from one set of roots. Some pears improve after picking, ripening slowly off the tree. A pear can be at its best when it is not fully ripe on the branch. If left too long, it may soften unevenly or become grainy at the center. Growers often pick pears when they are mature but still firm, then let time do the rest in a cooler, calmer space. During that wait, the interior changes quietly. Starches shift into sugars, aromas deepen, and the texture can turn from crisp to buttery without collapsing into mush. This is why a pear that tastes plain on day one can become fragrant and luxurious a few days later. Different varieties have different rhythms. Some need only a short rest. Others benefit from a longer pause, then a gentle finish at room temperature. In a sense, the pear is a fruit with a second act, and you get to witness the transformation in your own kitchen as it moves toward its sweetest moment. Cold storage can pause apple ripening for many months. An apple looks still, yet it keeps running a slow internal clock after harvest. Cold storage works by turning that clock down. Lower temperatures slow the chemical reactions that soften flesh, shift flavor, and break down acids, which helps an apple stay crisp far beyond its natural season DT. This is one reason apples can feel like a year-round fruit, even in places with hard winters. Long before modern refrigeration, people used cellars, ice houses, and cool barns to stretch the harvest, choosing varieties that stored well and stayed firm. Today, carefully managed cold rooms can hold apples for months while preserving bite and aroma. Not every apple behaves the same. Some varieties keep their snap with ease, while others lose firmness quickly and are better eaten fresh. Cold storage is not just convenience. It is a way of slowing time for a living fruit, keeping autumn's freshness available deep into winter. Controlled air storage can slow fruit breathing almost to a whisper. Temperature is only part of the story. Apples also breathe in a biological sense, taking in oxygen and releasing carbon dioxide as they use stored energy. Controlled atmosphere storage changes the air around the fruit, lowering oxygen and adjusting carbon dioxide to slow that respiration. It is like putting the fruit into a careful, safe, slow motion. The goal is to reduce the speed of aging without damaging flavor or texture. Too little oxygen can stress the fruit, so the balance must be precise. In advanced storage, sensors track conditions and adjust them over time, keeping the apples stable for long periods. This approach makes it possible to deliver crisp apples long after the harvest window, with less loss and less waste. It is also a reminder that post-harvest science is not about making fruit artificial. It is about understanding the fruit as a living system, then giving it conditions that encourage calm rather than haste. Fruit continues to respire after harvest, staying biologically alive. When fruit is picked, it does not become inert. Cells are still active, and they keep converting stored sugars and acids into energy. That process releases heat and water vapor, which is why piled fruit can warm up and why moisture can build inside boxes. Respiration also means the fruit is slowly changing from the inside. Texture loosens, aromas evolve, and the balance between sweetness and sharpness shifts day by day. This is why handling matters so much. Good ventilation can prevent heat buildup. Gentle cooling can slow change. Bruising can speed decay because damaged cells become easy targets for microbes. It is also why different fruits behave so differently on a counter. Some hold steady, others race ahead. Post-harvest life is a quiet continuation of plant metabolism, and every storage choice is a way of guiding that living process. Even in your kitchen, the fruit is still doing biology. Citrus segments are specialized juice sacs grown for seed support. If you pull apart an orange, you are opening a carefully engineered seed package. Each segment is filled with thousands of tiny juice sacs, which are like soft balloons grown from the inner wall of the fruit. Their job is not only to taste good. They store water and sugars that help keep the developing seeds safe from drying out. The sacs also make the fruit worth carrying because they offer a rewarding mouthful with every bite. The thin membranes between segments act like dividers, which helps limit damage if part of the fruit is bruised or invaded by microbes. Even the pith has a role because it cushions and supports the structure like padding in a travel case. The citrus interior is not random. It is a seed nursery built out of edible storage. A lemon tree can carry blooms, green fruit, and ripe fruit together. A lemon tree can look like it is living in several seasons at once. On one branch, a fresh flower opens with bright scent and pollen. Nearby, small green lemons sit hard and glossy, still building their acids and oils. Elsewhere, ripe fruit hangs heavy, ready to be picked. This overlap happens because lemon trees can flower more than once in a year when conditions allow, especially in mild climates with enough water and warmth. Instead of placing all its chances in a single window, the tree spreads its effort across time. That is useful when weather is unpredictable. A storm or heat wave might ruin one round, yet another round can succeed. For growers, it means a longer harvest and less risk. For you, it means the tree is always busy, quietly running a rolling schedule of blossoms becoming fruit. Oranges were once a luxury, shipped as precious winter sunshine. Before modern cold storage and fast transport, an orange in winter could feel like a miracle. In colder regions, fresh fruit was scarce when days were short, and vitamin-rich foods were harder to come by. Oranges traveled from warmer groves to distant cities, wrapped carefully to survive the journey and avoid bruising. They were often given as gifts, tucked into stockings, or saved for special moments because they were bright, fragrant, and rare. Peeling one released a burst of scent that felt like a small, personal sunrise. That emotional power mattered as much as the taste. An orange was proof that somewhere, even in the dead of winter, trees were still growing, and sunlight was still being stored in living flesh. The modern abundance is wonderful, yet it can hide how astonishing a winter orange once seemed. Pomelos are ancient citrus giants and ancestors of modern grapefruit. A pomelo is citrus in its oldest, most old-fashioned form. It can be as large as a melon, with a thick rind and big pale segments that feel almost architectural. What makes it even more fascinating is its family role. Pomelos are one of the original citrus types that helped give rise to many later fruits through natural mixing and human selection. When different citrus trees grow near each other, pollen can cross between them, and the next generation can carry blended traits. Over time, that blending created new fruits with new balances of sweetness, bitterness, and aroma. The grapefruit traces part of its lineage back to pomelo, which is why grapefruit can feel larger and more complex than a simple orange. When you taste pomelo, you are tasting a living ancestor. It is like meeting a grandparent and recognizing features you have seen in younger relatives. Grapefruit began as a natural citrus hybrid, not a designed invention. Grapefruit did not start as a carefully planned human creation. It appears to have emerged when two citrus types grew close enough for pollen to cross, producing offspring with a new personality. That is how many fruit surprises begin, with a chance meeting in an orchard or garden. Early growers noticed the result, then kept propagating it because the fruit was striking, large, and refreshingly sharp. The name reflects another surprise. Grapefruits can hang in clusters, and that bunching reminded people of grapes. Inside, the taste can feel like a tug-of-war between sweetness and bitter edge, which makes it stand apart from softer citrus. Over time, growers selected varieties that leaned sweeter or less bitter, shaping what most people know today. Yet the origin story remains charmingly accidental. A grapefruit is a reminder that nature can invent new foods without asking permission, then humans simply decide to keep the invention. Limes and lemons are complex hybrids shaped by human hands. Lemons and limes are not single, simple species that popped into existence fully formed. They are the result of citrus lines mixing over long periods, with people repeatedly choosing trees that produced useful fruit. In practice, that meant selecting for sharp acidity, strong aroma, and reliable harvests. Then propagating those trees so the traits stayed consistent. Over generations, this turned citrus into a kind of living toolkit. Need brightness for cooking, preserving, or drinks. Choose the tree that delivers it. Need a different balance of tartness and perfume. Choose another. The same process also explains why lime can mean different fruits in different places, each with its own scent profile and culinary role. What we call a lemon is not just a fruit. It is a history of gardens, trade routes, and taste preferences, written into a rind and a sour bite. The bitterness in citrus can come from the peel's defense chemistry. Bitterness is often the plant's way of saying, "Do not chew here." In citrus, the peel and the white pith beneath it contain compounds that can taste sharply bitter, especially if the fruit is unripe or the peel is damaged. These chemicals help defend against insects and microbes that would otherwise treat the fruit as an easy target. The fascinating part is how localized the bitterness can be. The juice may taste bright and pleasant, while the pith tastes harsh, like a warning layer. Processing can also change what you notice. When zest is grated thinly, you mostly capture fragrant surface oils. When pith is included, bitterness rises quickly. That is why marmalades, bitters, and citrus-infused spirits can range from refreshing to intensely sharp. The fruit offers sweetness for partners and bitterness for threats, and it stores each message in different layers. Pomegranates store jewel-like arils, each one a seed wrapped in juice. A pomegranate is less like a berry and more like a treasure chest. Inside its leathery shell, it holds hundreds of arils, and each aril is a seed wearing a cushion of juicy flesh. That structure changes how you eat it. You do not bite into one continuous body. You harvest it, bead by bead, like gathering rubies from a hidden chamber. The plant benefits from this design because every aril is a separate dispersal unit. An animal can eat a handful and move on, dropping seeds as it goes. The firm outer rind also helps protect the interior from drying out in hot climates, which is one reason pomegranates thrive where some softer fruits struggle to sprout. Even the sound is memorable, the crisp pop as an aril bursts. It is a fruit that turns eating into a ritual and turns seeds into something that feels almost precious. Pomegranate juice stains because pigments bind eagerly to fibers. That deep red is not just color, It is chemistry with staying power. Pomegranate juice is rich in pigments that dissolve in water and spread quickly into tiny gaps in fabric. Once they are there, they can cling to fibers and resist a casual rinse, which is why one splash can become a lasting mark. The same stubbornness is part of why the color looks so intense in the first place. The pigments are built to be stable enough to survive in a watery fruit environment and to remain vivid as the arils ripen. It is also why pomegranate has been used historically as a source of dye in some places, and why the juice looks almost like ink on a cutting board. There is a lesson hiding in that stain. Fruits are chemical factories, and their colors are not paint. They are molecules with real behavior, real bonds, and real consequences for your shirt. Cranberries float when ripe because air pockets form inside. Cranberry harvest can look like a magic trick because farmers can flood the bog and watch the fruit rise to the surface. Ripe cranberries develop small air spaces inside, which increases their buoyancy and lets them float. That makes wet harvesting possible because the berries can be corralled and collected efficiently as they bob in a red carpet across the water. The floating also hints at the cranberry's natural habitat. It grows in wet, acidic bogs where water is always part of the story, and a fruit that can move with water has advantages. The berry's skin is tough, which helps it handle bouncing, floating, and handling without splitting too easily. When you see photos of cranberry bogs, it looks almost unreal, like a lake turning into fruit. Underneath, it is a simple physical trick, and it is one that humans learn to use with perfect timing. Blueberries turn blue from a waxy bloom, not just pigment. A blueberry's color is a kind of optical trick. Underneath, the skin often carries dark red and purple pigments, yet the berry looks dusty blue because of a thin, waxy coating on the surface. That coating is called a bloom, and it scatters light in a way that shifts the appearance toward blue, almost like a natural filter. Rub a blueberry between your fingers, and you can see the effect change, because the bloom smears or wears away, revealing darker tones underneath. This is why freshly picked blueberries can look more blue than berries that have been handled a lot. The bloom is also why blueberries can seem to glow softly in the sun, even when the pigment itself is deep and wine-colored. It is a reminder that fruit color is not always paint. Sometimes it is structure, texture, and light behaving together. The waxy bloom also helps berries hold water and resist microbes. That dusty layer is not only for show. It is a protective coat that helps the berry manage its own survival after it ripens. Wax reduces water loss, which matters because a ripe berry is mostly water and can shrivel quickly in dry air. The bloom also makes it harder for some microbes to gain a foothold, because water does not cling as easily to a waxy surface. Less lingering moisture means fewer chances for molds to settle and spread. It can even reduce tiny abrasions from handling because the surface stays a little more slippery. This is why berries with an intact bloom often look fresher longer and why growers try to handle them gently. When you wash blueberries, you remove part of that armor, which is fine when you are ready to eat. The berry was not designed for a supermarket shelf. It was designed to last just long enough to be carried. Raspberries and blackberries are clusters of tiny fruits called drupelets. When you look closely at a raspberry, you can see it is built from many small bumps, and each bump is its own fruit. These bumps are called drupelets, and each one formed from its own tiny ovary in a single flower. That means a raspberry is not one simple fruit. It is a whole neighborhood of little fruits holding together in a soft dome. This architecture explains why raspberries bruise so easily. You are holding a structure made of many delicate units pressed together, with lots of juicy surfaces exposed. It also explains their intense flavor. Many drupelets mean many little pockets of juice, aroma compounds, and sugars concentrated into one mouthful. Even the hollow center has meaning. In raspberries, the drupelates detach from the core, leaving a space. The fruit is a bouquet of mini-fruits, designed to come apart. A blackberry is an entire handful of fruits, acting as one. A blackberry looks like a single berry, yet it is a cluster of drupelates just like a raspberry. The difference is in how it holds together. In a blackberry, the drupelates stay attached to the central core when you pick it, which is why the berry is solid rather than hollow. That core changes the eating experience. It adds a slight firmness and structure that can make blackberries feel more substantial on the tongue. It also changes how the plant handles dispersal. A fruit that stays intact can be carried farther before it falls apart, and it can withstand more squeezing from beaks and mouths. Blackberries also show how one basic flower plan can create different results with tiny structural tweaks. Hollow versus solid seems like a small detail, yet it changes texture, harvest, and the way the fruit travels. It is engineering at berry scale, and it is happening in a hedgerow. Cherries are drupes, built around one hard stone. A cherry's design is simple and bold. It builds sweet flesh around a single seed, then locks that seed inside a hard stone that is meant to survive chewing and weather. That stone is a protective capsule, and it allows the plant to offer a generous reward without sacrificing the embryo inside. This structure also shapes the cherry's texture. The flesh can be soft and juicy because the seed does not need to be protected by tough fibers throughout the fruit. Instead, the strength is concentrated in the pit. In nature, an animal can swallow a cherry, carry it, and drop the stone later, sometimes far from the parent tree. The pit can sit in soil through cold and wet, waiting for conditions to line up. When you eat cherries, you are meeting a strategy that shows up again and again in fruit evolution. One big promise, one armored seed, and a bright invitation. Peaches, plums, and apricots are drupes too, close cousins. Peaches, plums, apricots, and cherries belong to the same general fruit plan. And once you notice it, you see the family resemblance everywhere. Each one builds a juicy outer layer around a hard inner stone, and inside that stone sits the real seed. This shared structure helps explain why their flavors feel related, even when one is tart and another is honeyed. It also explains why their pits look similar, and why their blossoms often look similar in spring. The stone is a fortress that lets the fruit be soft and fragrant without putting the embryo at risk. These fruits have also been shaped by people in different directions. Some plums have thick skin for shipping. Some peaches have been bred for melting tenderness. Some apricots hold onto a bright acidity that wakes up the mouth. Under the variety, the blueprint stays steady. It is a family of fruits telling one evolutionary story with different accents. A mango's stone is a seed inside a woody shell. When you slice a mango, you hit that wide, flat core that feels almost like a piece of carved wood. That is the seed's shell, and it is more like a shield than a simple pit. The mango protects its embryo inside a tough, fibrous casing that can endure pressure and bites. Depending on the mango type, that casing can be thick and hairy with fibers, or smoother and tighter, yet its purpose stays the same. The fruit around it becomes lush and aromatic, which attracts animals and people to carry it. Meanwhile, the seed stays defended, ready for a chance to root. Mangoes can also surprise you with variation inside the shell. Some seeds are single, while others can produce more than one seedling, which means one fruit can contain the potential for multiple shoots. Even without noticing, you are eating a fruit built around a hidden life raft, wrapped in wood, waiting for soil and rain. Many fruits evolve tough rinds to endure falls from height. Fruit often has to survive gravity before it can recruit an animal. In forests, many fruits ripen high in the canopy, and when they drop, they may hit branches, stones, and hard ground. A tough rind is a simple way to protect seeds from that impact. It is also a way to slow dehydration, which matters when a fruit might sit for hours before something finds it. Thick skins can act like helmets, keeping the inner flesh from bursting and keeping microbes out a little longer. This is especially useful for fruits that are meant to be eaten after they fall, rather than plucked directly from a branch. A hard exterior can also help the fruit travel, because animals can carry it without crushing it immediately. Think of gourds, melons, and other thick-skinned fruits that can be transported long distances. The rind is not just packaging. It is shock absorption, water management, and seed protection rolled into one. Coconuts can travel by sea for long distances, still viable. A coconut is a seed with a built-in boat. The outer husk is full of fibers that trap air, which helps it float and cushions it against waves and rocks. Beneath that husk sits a hard shell, then a layer of food and water that can support the embryo for a long time. This design means a coconut can fall into the ocean, drift with currents, wash up on a distant shore, and still have a chance to sprout. If it lands in the right place, it can root above the high tide line and begin a new palm, far from its parent. That kind of dispersal can connect islands and coastlines across huge distances without birds carrying seeds and without humans planting anything. The coconut's success is not luck. It is physics and biology aligned. It is flotation, plus protection, plus stored resources, all tuned for travel. Coconuts are drupes, not nuts, despite the name. The word nut makes coconuts sound like hard-shelled snacks, yet botanically, they fit the drupe family. A drupe has an outer skin, a fleshy layer, and a hardened inner shell around the seed. A coconut follows that plan, just in an extreme form. The green or brown outer layer is the skin. The thick, fibrous husk is the fleshy middle, adapted for flotation rather than sweetness. The hard shell is the stony layer, and inside sits the seed with its stored food. This classification is not trivia. It helps explain why the coconut behaves the way it does. It is built to protect one large seed, not to scatter many small ones. It is also why coconut water is not the same as juice. It is part of the seed's internal supply, a resource meant to support germination. The coconut is not a nut pretending to be a fruit. It is a fruit pretending to be a nut. A date is a fruit adapted for deserts, storing sugar and water. In the desert, ripening is a race against dehydration, and this fruit plays it brilliantly. Its flesh concentrates sugars as it matures, which lowers the water activity and makes spoilage harder in hot air. That sweetness is not only a treat for animals and people. It is long-term energy stored in a form that can last through travel and dry seasons. The skin also helps, because it limits moisture loss once the fruit is fully mature. On the tree, clustered dates can hang through intense heat, then shift from firm to sticky as they finish. For humans, that natural preservation became a reliable food for long journeys, trade routes, and oasis life. Even when dried, it still carries minerals and a rich, caramel-like depth. It is a desert strategy you can hold in your hand, built to endure where softer fruits would fail. Figs are inverted flowers with blossoms hidden inside. A fig is not built like an open bloom that welcomes the wind. It develops as a hollow structure with a small opening, and the tiny flowers sit protected within. This changes everything about how it grows. The outer skin becomes the wall of a living chamber, and the interior becomes a crowded field of miniature blossoms that mature together. As the fig ripens, enzymes soften the walls, sugars rise, and the inside takes on that jammy texture that feels unlike most fruit. The crunch some people notice is linked to the many tiny seed structures, which come from that internal floral crowd. This architecture also means a fig can hide its most important work from the outside world until it is ready. What looks like a simple fruit is really a botanical room, built to shelter a secret garden. When you bite into a fig, you are tasting a flower arrangement turned inward. Some figs can ripen without pollination, depending on variety. Not every fig needs the same trigger to become sweet and full. In certain cultivated types, the fruit can develop and mature without fertilized flowers, which means growers can produce crops even where the usual bees are. Pollination partners are absent. This trait is one reason figs spread so widely in human agriculture, since the tree can be reliable in new regions. The result is often fruit with very few viable seeds, yet plenty of soft flesh and syrupy flavor. For the plant, this is an unusual gamble, because it invests heavily even when seeds are not being produced in the normal way. For people, it becomes a gift, because it turns fig growing into something closer to a consistent harvest than a fragile partnership. It also creates variety in texture. Some figs are densely seeded and crunchy. Others are smoother and more honeyed, shaped by development rather than fertilization. A kiwi fruit comes from a vine, not a tree. The kiwi's fuzzy skin can make it seem like a sturdy orchard fruit, yet it is made by a climbing plant that needs support. The vine sends out long shoots, then wraps through trellises and wires, turning a farm into a leafy ceiling. This growth style changes how the fruit is managed. Sunlight has to be balanced across the canopy so fruit can sweeten evenly, and pruning becomes a kind of choreography that guides where energy flows. Under the skin, kiwi flesh holds an intense green, studded with tiny edible seeds arranged in a ring. The flavor is bright and complex, with acidity that feels closer to citrus than to many berries. Because the fruit hangs from a vine, it can be protected from some ground-level pests, yet it is also exposed to wind and weather, which makes careful farming important. A kiwi is proof that tree fruit is only one chapter of fruit ecology. Kiwis were once called Chinese gooseberries before rebranding. Names shape expectations, and this fruit's modern identity is a marketing story with real consequences. Chinese gooseberry described origin and hinted at a flavor comparison, yet it sounded unfamiliar and a little awkward to many buyers. As commercial growing expanded, especially in places far from its native range, producers chose a new name that felt simpler and more memorable. Kiwi connected the fruit to a national symbol and gave it a compact label that fit on boxes and in conversations. That shift helped the fruit travel socially as well as physically, moving from niche curiosity to common produce aisle staple. It is a reminder that food is not only biology. It is culture, trade, and psychology. The fruit did not change its chemistry when the name changed. People did. A new word made it easier to try, easier to sell, and easier to love, which quietly reshaped global demand. Dragon fruit comes from a cactus that blooms at night. This fruit begins on a plant built for dry climates, with thick stems that store water and spines that deter hungry mouths. Then it does something unexpected. It produces huge blossoms that open after dark, often for a single night, with a scent strong enough to travel through warm air. By morning, those flowers wilt, and the ovary begins swelling into the vivid fruit you recognize, with bright skin and leaf-like scales. The plant's cactus nature helps it survive heat and scarce rainfall, yet the fruit it makes feels tropical and extravagant. Inside, the flesh can be white or red, speckled with tiny seeds that add a gentle crunch. The contrast is part of the charm. A cactus suggests harshness and restraint. This one produces a neon-colored fruit that looks almost invented. It is a reminder that desert adaptations do not always lead to plain designs. Sometimes they lead to spectacular ones. Some night-blooming fruit plants court moths and bats. When flowers open at night, they are speaking to a different audience. Bright daylight colors matter less, so many night blooms lean on scent, pale petals, and abundant nectar. Moths can follow fragrance trails in the dark, and bats can locate blossoms using smell and sound, then carry pollen as they feed. This creates pollination routes that most people never witness, because the work happens while we sleep. It also shapes flower form. Night-pollinated blossoms are often wide, sturdy, and easy to access, built for hovering wings or a quick bat visit. In some ecosystems, these nocturnal pollinators are essential because daytime heat can reduce activity or dry out pollen too quickly. The result is an entire hidden shift in the plant world, where reproduction runs on moonlight schedules. The next time you see a fruit, it is worth imagining the unseen nightlife that helped it begin. Durian smell is powered by sulfur compounds, a loud chemical signature. Few fruits announce themselves so boldly. The aroma can fill a hallway and people react instantly, either with delight or with retreat. That strength comes from a cocktail of volatile molecules, including sulfur-containing ones that travel easily through air and linger on surfaces. For the tree, this intensity may be useful because it can attract large animals from far away, even in dense forests where vision is limited. The smell becomes a beacon that says the fruit is ready, and it guides eager eaters to a heavy prize on the ground. Inside, the flesh can be rich and custard-like, with a flavor that some describe as savory sweet and complex, rather than simply sugary. This mismatch is part of why durian feels so strange. The outside message is aggressive. The inside experience can be luxurious. It is a fruit that forces you to pay attention, and that may be the point. In the forest, subtlety can be ignored. Many animals love durian, even when humans argue about it. In tropical ecosystems, strong smells are often invitations, and this fruit sends one of the clearest. Animals that rely heavily on scent can locate it quickly, then take advantage of its dense calories. Forest mammals, including some primates and civets, have been observed seeking out fallen fruit and feeding eagerly. For them, the aroma is not offensive. It is information. The thick husk also matters, because it protects the soft interior until the fruit is fully ready, then splits to reveal the reward. That timing can create a feeding event, where multiple creatures arrive and competition rises. Seeds benefit when pieces are carried off or dropped away from the parent tree. This is a different view of the famous smell debate. Humans often judge it by indoor standards, like trains and hotel rooms. Wildlife judges it by survival standards, like finding energy in a complex forest. The fruit was never designed for polite spaces. It was designed to be found. Jackfruit can grow enormous because it forms directly on the trunk. Some plants place fruit out on slender branches, yet this one builds its heavy prize against the strongest support it has. Growing directly from the trunk allows the tree to hold a fruit that can reach startling sizes without snapping limbs. It also changes who can access it. A trunk-borne fruit is easier for large animals to reach, and once it drops, it becomes an event on the forest floor. Inside, the fruit is made of many compartments, each surrounding a seed with a fragrant, chewy bulb of flesh. The smell can be sweet and strong, and the texture can mimic pulled meat when unripe and cooked, which is why it has become famous in savory dishes. Its size is not only spectacle, it is a strategy. One huge fruit can carry many seeds at once, packaged in a form that invites sharing across an entire ecosystem. The trunk is the anchor, that makes the whole design possible. Fruit can grow on trunks because flowers emerge from older wood. Some trees do not place every flower at the twig tips. Instead, they can bloom straight from older branches or even the main trunk, a pattern called cauliflory. It looks surprising, like fruit has been pinned directly to the bark. Yet it makes practical sense. Heavy fruits can be supported by thick wood, which reduces the risk of snapping slender branches. Trunk-level fruit can also be easier for large animals to reach, which matters when those animals are the best seed carriers. In dense tropical forests, trunk fruit can be easier to spot and smell at close range, especially when the canopy is crowded with leaves. It is also a clever way to use space. The outer canopy can focus on leaves and light capture, while the trunk becomes the stable platform for reproduction. When you see fruit growing from bark, you are seeing an architectural decision made by evolution. Bananas grow upward because the stalk bends as it expands. A banana bunch begins on a long stalk that points downward, and the developing fruit first hangs like many other heavy structures. Then, something dramatic happens. As the bananas grow, the stalk curves, and the fruit gradually turns upward toward the light. This upward bend helps the fruit avoid shading itself and can improve exposure to warmth and sun. It also changes how rain runs off, which can reduce the time water sits on the developing peel. The curve is a growth response, not a conscious choice, yet it gives the bunch that iconic shape that looks like it is reaching. If you have ever seen bananas still on the plant, the effect can feel almost theatrical. The bunch forms low, then reorients as it develops, as if the fruit is adjusting its posture mid-performance. That motion is a reminder that plants are not static sculptures. They move, slowly and purposefully, through growth. The banana plant is a giant herb, not a true tree. It can tower above you like a tree, yet it does not build a woody trunk. What looks like a trunk is actually a pseudostem made from tightly wrapped leaf bases, stacked and compressed into a sturdy column. This matters because it changes the plant's life cycle. After producing one bunch, that above-ground stem dies back, and new shoots rise from the underground corm to continue the line. The plant is built for speed and replacement rather than long-lived wood. This is part of why banana groves can look so lush so quickly. Leaves unfurl like flags, wide and fast-growing, turning sunlight into biomass with impressive efficiency. It also means storms can tear leaves more easily than they would on a woody tree, yet the plant can recover by pushing out new growth. When you stand beside a banana plant, you are standing beside a herb that learned to grow big, tall, and dramatic without becoming wood. Pineapple plants can take years to fruit, then fruit once. A pineapple plant spends a long time preparing for its one big show. It grows as a rosette of stiff leaves, slowly storing energy, building roots, and gathering sunlight day after day. Only when it reaches the right size does it shift into reproduction. Then a flower stalk rises from the center, blooms in a tight cluster, and begins forming the fruit we recognize. After that, the plant does not keep fruiting in endless cycles. It has made its major investment, and its energy turns toward producing offshoots, which are little clones that can become new plants. This strategy can feel patient, almost stubborn. Years of preparation, then one concentrated reward. For farmers, it means timing is everything. For the plant, it is a way to ensure it has enough resources to build a large, attractive fruit that will be eaten and spread. The pineapple is proof that some fruits are the finale, not the ongoing routine. A pineapple crown can be replanted to grow a whole new plant. That spiky tuft on top is not decoration. It is a living cluster of leaves with a growing point, and it can become the start of another pineapple plant. If you twist off the crown, let it dry a little, and place it in soil, it can produce roots and begin a slow new life. This is vegetative propagation in your own kitchen, a reminder that fruit can carry more than seeds. It can carry ready-made plant tissue prepared for the next chapter. The crown is adapted to survive handling and transport, and that toughness makes it surprisingly willing to root if given warmth and patience. Over time, the new plant forms the same rosette shape and follows the same long preparation before it fruits. Planting a crown feels like a small act of time travel. You eat the fruit now, then you start the next fruit years ahead, using nothing more than what would otherwise be compost. Some fruits ripen by softening cell walls, turning crisp to tender. Ripening is not only about becoming sweeter, it is also about texture changing in a controlled way. Many fruits begin firm because their cell walls are tightly linked, creating a structure that resists pressure. As ripening begins, the fruit activates its own tools for remodeling. Connections between wall components loosen, water shifts within tissues, and the fruit yields more easily under a bite. This is why a hard peach can become meltingly soft, and why a pear can transform from crunchy to buttery. The fruit is essentially dismantling some of its own scaffolding on schedule to become more attractive to eaters at the moment seeds are ready. It is also why ripening can feel sudden. Once the softening process crosses a threshold, texture changes quickly. In your hand, it seems like magic. Inside, it is chemistry, doing construction work in reverse, turning a protective structure into an edible invitation. Fruit softness is chemistry, controlled by enzymes that remodel pectin. Pectin is one of the key substances that helps plant cells stick together, and it is a major reason unripe fruit can feel hard. During ripening, the fruit produces enzymes that change pectin's structure, breaking it into smaller pieces that do not hold tissues as tightly. The result is a shift you can feel. A fruit that once resisted your fingers begins to yield, and then to bruise if handled roughly. Different fruits use different mixes of enzymes, which is why a ripe mango feels silky, while a ripe apple often stays crisp. This chemistry is also why ripening is sensitive to temperature. Warmth can speed enzyme activity, while cold can slow it. The process is not random, and it is not just decay. It is a planned softening that makes the fruit more appealing to animals at the right moment. The fruit is not falling apart by accident. It is rewriting its own texture on purpose. The snap of a fresh apple comes from pressurized cells. That crisp crack you hear is a physical event happening at tiny scales. Apple flesh is made of many cells filled with water, and those cells are under pressure, like microscopic water balloons packed together. When you bite, the cell walls rupture in quick succession, releasing juice and producing that clean, sharp snap. The structure also includes small air spaces that contribute to the sensation, making the bite feel light and crunchy rather than dense. As an apple ages or is stored poorly, it can lose water, pressure drops, and the bite becomes softer and less lively. That is why a truly fresh apple can feel almost startling, as if it is alive in your mouth. The sound is part of the experience, and it is also information. It tells you the tissues are still tight, still hydrated, and still holding their internal tension. Crunch is not just taste. It is physics, pressure, and structure announcing freshness. Fruit browning is a protective reaction triggered by damaged tissues. When you cut an apple or bruise a banana, the brown color can look like failure. In many cases, it is closer to a defense reflex. Inside the fruit, certain compounds and enzymes are kept apart in separate compartments. Damage breaks those boundaries, and when the components meet oxygen, reactions begin that create darker pigments. Those pigments can help seal the wound chemically, and they may make the damaged area less appealing to some microbes and insects. Browning is the fruit's version of closing ranks after injury, even though it happens after harvest too. The speed varies by fruit and variety, because the levels of the reacting compounds differ. It is also why careful handling matters. The more cells are crushed, the more reaction sites open up. What you see as discoloration is a biological response to exposure, a reminder that the fruit is built to defend itself, even after it has been picked. Lemon juice can slow browning by changing the chemistry of enzymes. A squeeze of lemon can keep apple slices looking brighter, and the reason is not a kitchen myth. Browning enzymes work best within certain chemical conditions, and lemon juice shifts those conditions. Its acidity can reduce enzyme activity, which slows the chain of reactions that produce brown pigments. Lemon also brings compounds that can act as antioxidants, which means they can react with oxygen-related intermediates before pigments form. The result is not permanent, yet it buys time, which is why lemon is used on cut fruit platters and in some preserves. This is a small example of chemistry you can taste and see. You are not masking color with flavor. You are altering the reaction pathway inside the exposed tissues. It is also a reminder that many culinary traditions are based on real mechanisms discovered through experience long before modern explanations. A simple citrus squeeze becomes a practical tool, turning a fast browning process into a slower, more manageable one. The spiciness of chili fruit is a deterrent aimed at mammals. Heat is not a flavor accident. It is a chemical boundary line. Chili plants make capsaicinoids, which bind to pain and heat receptors in many mammals, turning a bite into a strong warning. That deterrent can protect seeds from being destroyed by chewing, since many mammals grind food thoroughly. The brilliant twist is that the plant still wants someone to carry those seeds away. So it discourages the wrong couriers rather than discouraging everyone. The heat is concentrated in internal tissues near the seeds, which makes the message hard to ignore. In the wild, this can reduce losses to fruit-stealing mammals that might eat and crush everything close to the parent plant. For humans, the same signal became a thrill and a tradition. Yet for the plant, it is simply strategy. A chili is a fruit with a built-in bouncer, guarding the seed's future. Birds ignore chili heat, so they spread seeds safely. Many birds can eat hot peppers with no sign of discomfort. Their pain receptors respond differently to the compounds that make mammals gasp, so the fruit's warning sign is invisible to them. This is perfect for the plant. Birds often swallow fruit quickly, which means seeds are less likely to be crushed, and they can travel far before being dropped. A bird can cross gaps that a ground animal never will, carrying a seed to a new hillside, a riverbank, or a forest edge where sunlight is better. This also shapes where wild chilies can appear, sometimes popping up in places that seem oddly random until you remember flight paths and perching spots. The plant has essentially chosen a delivery service that does not chew much, moves fast, and covers distance. That choice is written into the fruit's chemistry. To a mammal, the pepper says stop. To a bird, it says dinner. Some fruits imitate leaves when unripe, hiding from hungry eyes. Unripe fruit often has a problem. It is not ready, but it is still edible enough to be stolen. One solution is disguise. Some fruits stay green, keep a matte surface, and blend into the canopy so well that even a close look misses them. The plant is buying time, because early removal means seeds are not mature and the investment is wasted. Camouflage can be surprisingly convincing, especially in dense foliage where shadows break up shapes. As ripening begins, the disguise drops. Pigments rise, shine increases, and scent strengthens, turning the hidden fruit into an obvious target. This timing creates a clean signal. Before, it says nothing to most eyes. Later, it becomes a loud invitation that says, "Now is the moment." The change can feel sudden because it is meant to be sudden. A fruit that stays secret until it is ready is a fruit that keeps control of its own schedule. Some fruits drop when ripe, trusting gravity and animals below. Not every fruit is meant to be picked from a branch. For some plants, ripeness is the moment the fruit lets go. It softens at the stem, the connection weakens, and gravity does the harvesting. On the ground, the fruit becomes easier for large animals to find, and the smell can spread close to the soil where many noses search. Dropping also moves seeds away from the canopy, which reduces the chance they will sprout in deep shade under the parent. There is risk because the fruit can bruise or be eaten by the wrong creatures. Yet some fruits are built for impact with thick skins or springy flesh, and they ripen to a point where falling is part of the plan. If you have ever heard fruit thudding in an orchard, you have heard reproduction in motion. The tree is releasing a package, and the forest floor is the next stage of the journey. Some fruits explode open, flinging seeds with spring-loaded force. Some plants do not wait for animals at all. They use stored tension. As the fruit dries, its tissues shrink at different rates, building mechanical stress like a bent spring. At the right moment, the structure snaps, and seeds are launched outward in a sudden burst. This is called ballistic dispersal, and it can throw seeds far beyond the shadow of the parent. It is also startlingly precise. The fruit's walls are built to split along weak seams, guiding how the force is released. In a quiet patch of vegetation, you can sometimes hear the tiny crack of a pod letting go, like a miniature firework. The advantage is speed and independence. The plant does not need a courier with wings or fur. It uses physics and dryness, turning sunlight and water into stored tension, then into motion. It is a reminder that plants can move their offspring without moving themselves. The pop of a ripe pod is stored tension released. That sudden sound is the end of a slow buildup. As a pod matures, its walls change in thickness, moisture, and stiffness. When the outer layers dry, they contract, yet inner layers may resist or contract differently, which creates a twisting force. The pod is quietly loading energy over days. Then, a threshold is reached. A seam gives way, the walls curl back, and seeds are hurled into the air or scattered across the ground. The pop is brief, yet the preparation is long. This is why you might find pods that seem calm for weeks, then suddenly empty. For the plant, the timing is useful. A dry, sunny moment is often better for seeds to travel and settle than a damp one. The pod is acting like a self-timed machine, waiting for the right conditions to turn tension into dispersal. The sound is not drama. It is mechanics, completing a plan. Fruit can be a timed gift, matching animal migrations. In many ecosystems, plants and animals keep each other's calendars. Fruit ripening can be synchronized with the arrival of seasonal travelers, turning a forest into a refueling station at exactly the right time. When migrating animals arrive hungry, they eat heavily, and seeds get carried quickly across long routes. That movement can connect distant habitats, spreading plants beyond their usual neighborhood. For the animals, fruit can be the difference between making the next leg of a journey or failing. For the plant, it is a moment of high-efficiency dispersal, when couriers are abundant and mobile. Timing can be tuned by day length, temperature, and rainfall, which means the plant is responding to the same seasonal cues that guide migration. When you see trees loaded with ripe fruit in a narrow window, it can be more than coincidence. It can be an appointment kept across species. The plant offers energy, and the travelers repay it with distance. In many forests, fruit seasons choreograph whole animal calendars. A forest is not only a collection of trees, it is a schedule. When certain fruits ripen, animals adjust their movements, their feeding times, and even their social behavior. A troop may travel farther each day to reach a favorite patch. Birds may shift nesting timing to coincide with abundant food. Insects can surge when fruit is plentiful, and that can draw in predators that follow the insects. One fruiting tree can become a meeting point, noisy with wings and calls, then quiet again when the crop is gone. This creates pulses of abundance that ripple through the ecosystem. It also means that a bad fruit year can echo outward, changing survival rates and migration routes. Fruit is not a side dish for the forest. It is one of the clocks that tells animals when to move, when to rest, and where to gather. If you want to understand a forest, follow the fruiting seasons. You will find the living timetable. Fruit scarcity can push animals to travel, spreading seeds farther. When fruit is plentiful, animals can feed close to home. When it is scarce, they have to widen their search. That search can turn into long-distance dispersal for plants because hungry animals keep moving until they find a new supply. Seeds consumed during a lean period may be dropped far from the parent, simply because the courier was forced to roam. Scarcity can also change what animals choose to eat. They may accept fruits they normally ignore, which gives those plants a rare chance to be dispersed. This creates a strange partnership where hard times can increase seed travel, even while overall food is lower. It is not a comforting idea, yet it is ecologically powerful. The landscape becomes stitched together by movement driven by need. A seed that would have landed nearby in a rich season might end up in a distant clearing during a poor one. In that way, scarcity can act like a wind, pushing life outward through animals on the move. Fruit abundance can reshape ecosystems, feeding insects, birds, and mammals. A heavy fruiting season can feel like a feast, and it can ripple through many layers of life. More fruit means more insects, because sugars and yeasts attract swarms. More insects can mean more birds, which can mean more predators that follow the birds. Mammals may change their ranges to stay near reliable fruit sources, and their droppings can fertilize the soil in new patterns. Even the ground can change, because fallen fruit feeds microbes and alters nutrient cycles, which can influence what seedlings survive next season. Abundance is not only about well-fed animals. It is about shifting relationships. Competition changes when food is easy. Some species breed more successfully. Others arrive from elsewhere to take advantage. In extreme cases, a single species of fruiting tree can create a seasonal hotspot that reorganizes movement across an entire region. Fruit is energy made visible, and when it arrives in floods, the ecosystem responds like a living crowd. Everything gathers around the sugar. Many fruits protect themselves with tannins that taste dry and bitter. That dry, mouth-puckering feeling is not a mistake. It is a plant's way of discouraging early snacking. Tannins bind to proteins in saliva, which changes the way your mouth feels and makes unripe fruit less pleasant to keep eating. This can protect seeds while they are still developing, because an animal that dislikes the texture may move on before doing much damage. Tannins also make life harder for many microbes and insects, which helps fruit resist rot and pests during a vulnerable stage. You can taste this defense in astringent persimmons, underripe bananas, and some young grapes. The plant is using chemistry as behavior control. It cannot chase a thief away, so it makes the thief's mouth uncomfortable. Later, when the fruit is ready, the balance shifts. The warning fades, and the invitation takes its place. That one sensation on your tongue is a negotiation between your appetite and a plant's timetable. Tannins often fade as fruit ripens, signaling safety to eat. Ripening is a shift from warning to welcome. As sugars rise and aromas open, tannins often become less noticeable, either because their chemistry changes or because sweetness and softness overwhelm the old bee. Dryness. To an animal, this is useful information. It means the fruit is now worth the effort, and the seeds inside are likely mature enough to survive the trip. Some fruits make this contrast dramatic. An astringent persimmon can feel almost inedible at first, then suddenly become silky and honeyed when fully ripe. That change can guide eating behavior without a single word. It creates a built-in "not yet" and "now" signal that travels through taste. The plant benefits because animals are more likely to eat at the optimal moment, then carry seeds away. The animal benefits because it avoids wasting time on unripe, less nutritious food. Ripening is not only about getting sweeter. It is about becoming trustworthy. Some fruits keep toxins in leaves but spare the ripe flesh. A plant has to defend itself all year, not only during harvest season. Leaves are exposed for months, and they're constantly at risk of being eaten before the plant can gather enough sunlight to survive. So many plants load leaves with stronger deterrents than they put in ripe fruit. The fruit has a different mission. It needs to be eaten, so it often reduces harsh defenses in the flesh once seeds are ready. That does not mean the plant becomes harmless. It means it becomes selective. You can see echoes of this strategy in the way some fruit parts are avoided while others are enjoyed. Leaves, stems, and unripe tissues may remain unpleasant, while the ripe flesh becomes inviting. It is a careful balance between protection and partnership. The plant is guarding its solar panels while advertising its seed package. In that split strategy, you can hear evolution thinking in two directions at once. A fruit's acidity can protect it from microbes and spoilage. Acid is part flavor, part armor. Many microbes struggle to thrive in low pH environments, so a sour fruit can be a tougher place for spoilage organisms to take over. This is one reason some citrus and tart berries can hold up better than you might expect, especially when their skins are intact. Acidity also shapes how we experience ripeness. A fruit can be sweet and still feel bright because acid keeps the flavor from going flat. For the plant, that brightness can be useful. It may slow decay long enough for an animal to find and carry the fruit, and it may steer the fruit towards certain eaters that tolerate sourness. Even after harvest, acidity influences preservation traditions. People have long used sour fruit and acidic preparations to keep food safer because many harmful microbes are less comfortable in acidic conditions. When you taste that sharp edge, you are tasting a survival tool. The fruit is not only offering sugar, it is setting boundaries for what can live inside it. The sweet smell of ripe fruit can be a microbial battleground. That delicious perfume floating off a ripe fruit is also a beacon for organisms you cannot see. Yeasts and bacteria can sense those sugars and begin colonizing tiny cracks, pores, and bruises. Some microbes are helpful because they can outcompete more dangerous ones or start controlled fermentation. Others cause fast rot, turning a perfect peach into a soft collapse. The fruit is not helpless in this fight. It has acids, protective skins, and chemical defenses that slow invaders, at least for a while. Yet once ripeness peaks, the balance often shifts toward the microbes, because the fruit is rich in water and easy energy. In nature, this can still serve the plant. A strong smell can draw animals quickly, which reduces the time microbes have to win. In your kitchen, the same smell is a countdown. Fragrance is often the first sign that a race is underway. Yeasts and bacteria compete on skins, shaping flavor and rot. A fruit's surface is like a tiny ecosystem. Invisible communities arrive from air, soil, insects, and hands. And they do not all want the same thing. Some yeasts thrive on sugar residues and produce fruity aromas as they grow. Some bacteria create sour notes, softening tissues or producing off smells. They compete for space and food, and the winner can change what the fruit becomes. This is why the same fruit can behave differently in different places. Local conditions and local microbes can steer whether a fruit stays fresh, ferments pleasantly, or spoils quickly. It is also why a small bruise matters. Damage opens pathways into the flesh, turning a skin-level contest into an internal invasion. In the world of winemaking, this surface life is celebrated because it can drive fermentation and complexity. In a lunchbox, it can be the start of decay. Either way, the fruit is never truly alone. Its skin is a living frontier where microbes bargain, battle, and transform flavor. Fermentation can make fruit safer by preserving it without refrigeration. When fruit is abundant, it can spoil faster than people can eat it. Fermentation became a clever way to turn a short-lived harvest into something that lasts. Yeasts consume sugar and produce alcohol and other compounds that many harmful microbes dislike. In other ferments, lactic acid bacteria dominate and produce acidity that helps keep spoilage organisms in check. The fruit changes taste, texture, and aroma, and it also changes risk. What was once a fragile, easily spoiled food becomes more stable, sometimes for months. This is why so many cultures have fermented fruit traditions, from cider and wine to preserved fruit pastes and sour fruit drinks. Fermentation is not simply letting food go bad. It is guiding which organisms get to win. People learned to favor the microbes that protect food and create appealing flavors, then repeated the process until it became reliable. It is a partnership with the invisible world, using biology to keep sweetness safe. Dried fruit is preservation by removing water microbes need. Microbes love water. Take water away, and most spoilage slows dramatically. Drying does exactly that, concentrating sugars and reducing the moisture that molds and bacteria need to grow quickly. This turns fruit into something portable and durable, which helped travelers, sailors, and desert communities long before modern packaging existed. Drying also changes the eating experience. Flavors become deeper and more concentrated, textures become chewy, and aromas can shift toward caramel and spice notes. In some cases, the sun does the work, and the fruit dries in open air. In other cases, smoke, warmth, or controlled heat is used to achieve a predictable result. Either way, the principle is the same. You are changing the environment so microbes struggle, while the fruit's energy remains available. It is preservation through physics rather than through additives. A grape becomes a raisin. A plum becomes a prune. The sweetness stays, and time slows down. Fruit sugars can crystallize, creating textures like dates and dried mango. When fruit dries, sugars become more concentrated, and sometimes they begin to form tiny crystals. This can create a subtle crunch or a sandy texture, especially in fruits that are very sweet and low in water. In dates, you might notice a faint graininess that feels like nature's candy because sugar has started arranging itself into solid structures. In dried mango, crystallization can add a delicate bite that contrasts with the chew. This is not spoilage. It is a physical shift as molecules crowd together and find stable patterns. Temperature changes can encourage it, and storage conditions can influence how quickly it appears. Crystallization can even change how flavor hits your tongue because crystals dissolve at different speeds than syrupy sugars. The result is texture as chemistry, sweetness becoming architecture. It is another reminder that fruit is not just taste. It is matter changing state, quietly turning liquid sweetness into something you can feel between your teeth. Jam sets because pectin forms a network with sugar and acid. Jam is a transformation that feels like magic, yet it is careful structure building. Many fruits contain pectin, a plant substance that can link together into a gel when conditions are right. Sugar helps by drawing water away, which allows pectin chains to connect more easily. Acid helps by adjusting the electrical charges on those chains so they can come close and form a stable network. When the mixture cools, that network traps water and fruit pieces, turning a pot of bubbling liquid into a spreadable set. This is why some fruits make jam more easily than others, and why cooks often add lemon juice to help things firm up. Jam is not simply fruit made thicker. It is fruit chemistry rearranged into a new texture that resists flowing. It is preservation, flavor concentration, and molecular architecture all at once. When you spread jam on toast, you are spreading a carefully built pectin scaffold that holds summer in place. Pectin levels differ by fruit, which is why some jams struggle. If you have ever cooked fruit and wondered why it stayed runny, pectin is often the reason. Some fruits naturally carry plenty of it, especially when they are slightly underripe. Others contain much less, so their juices refuse to hold a firm shape. That difference is why a pot of apple or quince can thicken confidently, while a pot of strawberries can remain loose unless you help it. It also explains why jam makers pay attention to variety and ripeness, not just sweetness. The fruit is bringing its own setting power, and it can vary widely from batch to batch. Even within one fruit, the parts differ. Skins and cores can contribute more structure than pure juice. When jam struggles, it is not stubbornness. It is chemistry that simply did not arrive in high enough concentration to build a stable gel on its own. Citrus peels are pectin-rich, so marmalade can set so well. Marmalade is unusual because it does not rely only on fruit pulp. It asks the peel to do the heavy lifting. Citrus peel carries a high load of natural gelling material, especially in the white layer just beneath the colored rind. When pele is simmered, those substances can move into the liquid and help it firm as it cools. That is why marmalade can achieve a beautiful set, even when the jar is packed with glossy slices and a lot of juice. The peel also brings fragrance and a gentle bite, which makes marmalade feel like a conversation between sweet and sharp. Good marmalade is not simply orange jam with strips. It is a peel-driven preserve built around the pulps of the fruit that most people throw away. In that way, marmalade turns citrus architecture into texture. It uses the fruit's outer defenses to create a lasting, spoonable structure. Fruit seeds often carry oils, meant for a seedling's first push. A seed is not only an embryo, it is an emergency kit. Many seeds store energy as oil because oil packs a lot of calories into a small space. That matters when a seed sprouts and has no leaves yet, since it cannot harvest sunlight until it grows upward and unfolds green tissue. The oil becomes fuel for roots, stems, and the first fragile leaves. This is why some seeds feel rich or nutty when you taste them, and why a cracked seed can have a faint, oily sheen. It is also why seeds can stay viable for long periods. Dense stored energy helps an embryo survive delays, whether it is waiting through a dry season or a cold one. When you see a seed as a potential plant, the stored oil becomes easier to appreciate. It is the first packed lunch of a new life, sealed for the moment growth begins. The scent of an orange peel is a fast chemical defense. That bright burst you smell is not only for human pleasure. It is part of the orange's quick response system. When the peel is scratched or broken, aromatic compounds escape rapidly into the air, and many of them are unfriendly to fungi and small pests. The smell spreads fast, which matters because a damaged fruit is a tempting entry point for microbes. These compounds can slow growth on the surface and discourage some insects from lingering. They can also mask the smell of sugary flesh, which may reduce attention from animals that would damage the fruit before the seeds are ready. Humans have noticed the same power in other contexts. Citrus oils have been used for cleaning and for keeping certain foods fresher, because the chemistry is active rather than decorative. When you peel an orange and the room fills with scent, you are witnessing a defense cloud. The fruit is reacting to injury by changing the air around it. Some fruits are bred for travel toughness, not just taste. The fruit you buy is often selected for a journey you never see. It must survive picking, sorting, packing, transport and storage, and it must arrive looking appealing. That pressure can favor thicker skins, firmer flesh, and resistance to bruising, even if those traits slightly reduce fragrance or melt in the mouth softness. Tomatoes are a clear example, since a variety bred for shipping can be sturdy enough to stack, while a garden type may be too delicate to travel. Peaches can face the same trade-off. A fruit that ripens to perfect softness on the tree can collapse in a crate. Breeding for toughness is not villainy. It is problem-solving for distance. The surprise is how much it shapes what people think fruit is supposed to taste like. Many of the most intense flavors live in fruits that do not travel well. When you find a fruit that feels unusually fragrant, it may be because it was grown for closeness rather than logistics. Modern supply chains can pick fruit green, then trigger ripening later. For many fruits, timing is a balancing act between flavor and survival. If fruit is picked fully ripe, it may bruise or spoil before it reaches a distant store. So, supply chains often harvest at a mature but firm stage, then manage ripening closer to where the fruit will be eaten. Ripening rooms can control temperature, airflow, and natural ripening signals, so fruit softens and sweetens on a schedule. This lets a banana arrive firm and finish later, or lets a tomato turn red during transport rather than in the field. The result is reliability. Stores can stock fruit consistently, and waste can be reduced. The trade-off is that some flavors develop best on the plant, where sunlight and daily temperature swings continue feeding the fruit. Modern ripening is a practical compromise, and it is one reason local, tree-ripened fruit can taste different. The fruit is being guided, not faked, yet the path matters. A banana's flavor changes as starch converts into sugars. A green banana is not sweet by accident. It is sweet later by design. Early on, much of its energy is stored as starch, which is why unripe bananas taste mild and feel firmer. As the banana ripens, enzymes break that starch down into simpler sugars, and sweetness rises quickly. This is also when the aroma becomes more noticeable, since many scent compounds increase as the fruit matures. The texture shifts too. The flesh becomes softer as internal structure changes, which makes ripe bananas easy to mash and blend. The peel tells the story on the outside. Green becomes yellow, and brown speckles appear as the fruit continues to change. Those speckles are a sign that ripening is moving into a new stage, where sweetness can deepen and flavors can take on a richer, more caramel-like tone. When you choose a banana at the store, you are choosing a point on a moving timeline. The fruit is still transforming. Fruit can be climacteric or non-climacteric, changing how it ripens. Some fruits have a dramatic ripening surge, while others stay more steady. Climacteric fruits continue ripening after they are picked, and they often show a burst of internal activity as they soften and sweeten. Bananas, apples, and many pears fall into this group, which is why they can be harvested firm and finished later. Non-climacteric fruits behave differently. They do not improve much once removed from the plant, so they need to be picked closer to peak flavor. Many berries and citrus are in this category, which is why a dull, underripe strawberry rarely becomes wonderful on a counter. This difference changes everything about farming and shopping. It influences harvest timing, shipping methods, and how you should store fruit at home. It also explains why some fruits respond well to being kept near ripening companions, while others do not. Knowing the category turns fruit care into something more predictable. You start treating ripening as biology, not mystery. A grape's bloom can carry the yeast that starts wine. That dusty coating on a grape is more than a protective surface. It is also a place where microscopic life can cling and travel. Yeasts can settle there after arriving on wind, insects, and vineyard dust, and they can ride along until the grape is crushed. Once juice is exposed, those yeasts have access to sugar and oxygen, and they can begin multiplying quickly. This is one reason some winemakers handle grapes gently and avoid aggressive washing. They want to preserve the grape's native surface community. It is also why different vineyards can produce different fermentation behavior, even with the same grape variety. The local microbial cast can influence early aromas and the speed of fermentation. Grapes are not just ingredients. They are small habitats that carry their own companions. When you look at grape bloom, you are looking at a skin-level world that can help turn fruit into something entirely new, shaped by place in a way you cannot see. Every fruit is a plant's story of survival, written in sweetness and seeds. A fruit is never only a snack. It is the plant's way of turning reproduction into a partnership with the living world around it. Some fruits whisper with subtle fragrance. Others shout with color, fawns, thickness, or heat. Each one is shaped by the threats it faced and the allies it recruited, from microbes on skins to animals that travel far. Inside, the goal remains steady. Protect the embryo. Feed it at the start. Move it away from competition. The details are where the stories differ. A berry may bet on speed. A coconut may bet on endurance. A fig may hide its flowers inside a chamber and trust a specialist to find the door. When you eat fruit, you are participating in that strategy, whether you plant a seed, compost a peel, or carry a snack across town. The plant is reaching into your world, using flavor as a bridge. And in that bridge, you can hear evolution speaking. As we come to the end of our journey through fruit, you might notice how the ordinary has started to feel a little more surprising. A strawberry that is not truly a berry. A banana that is. An apple that began as a flower's base, swelling into crisp sweetness. Citrus built from countless juice sacs, each one a soft storehouse for seeds. Grapes carrying invisible partners on their skins. Peels that release fragrant defenses. Seeds that travel by birds, by waves, and sometimes by pure spring-loaded force. Tonight we wandered through orchards and jungles, through deserts and bogs, and through the quiet chemistry that makes ripening feel like magic. We followed the ways fruit signals to the world, with color, scent, tartness, and time. We noticed how plants invite the right helpers, discourage the wrong ones, and keep their futures tucked safely inside. If you enjoyed this slow exploration, you're warmly invited to like, subscribe, or share a thought below. It helps this little corner of science reach more sleepy listeners. And if you happen to still be awake, there will be another video waiting on the screen, ready to carry you onward into a new world of wonder. But for now, you can let the ideas settle. Let your shoulders soften. Let your breathing find an easy rhythm. Imagine a bowl of fruit resting in dim light, colors softened, scents faint in the air. Nothing to solve, nothing to do. Just the simple feeling of having wandered somewhere interesting and returned with your mind a little quieter. Sleep well and good night.